Welcome to EDU World Space.
Okay, in this problem we have a guy with a flashlight shining it into a body of water, some distance we call L1 away. When going from air to water, it refracts, and ultimately the light hits the bottom of this body of water, this pool, at some total distance away from the edge. So here's a picture of what's happening here. We have the flashlight some height above the water, H1, and then the depth of the pool is we're gonna call H2. And then the light, as it goes from the flashlight to the water, travels some horizontal distance L1. And when it goes through the water, it'll travel more of a horizontal distance L2 until it hits the bottom. And due to the refraction, we have an initial angle θ1 and a final angle θ2, which we can solve for by going through the refraction. And ultimately, we want to figure out the total distance that the light travels. So we're going to call that L, and it's equal to L1 plus L2 for these two separate right triangles that you can see. So to start us off, we're going to need Snell's law and a lot of trigonometry. Snell's law for refraction says that the index of refraction, N1, times the sine of the incident angle, θ1, is equal to the index of refraction going through the medium and the angle of refraction. So this is Snell's law. We're going to be making use of it. And then the rest of this is going to be a bunch of trig. So let's jump into it. So to start, we can determine the incident angle of the light as it goes from the flashlight to the water by just taking the tangent of that first right triangle. The tangent of the incident angle is just the opposite over the adjacent of that right triangle, which is L1 over H1, which we both happen to know. It's 2.5 meters over 1.3 meters, which gives us 1.923. And then to get the angle out of that, we can just take an arctan, which will give us 62.526 degrees. So that's the incident angle of the light. Now, at this point, we can apply Snell's law. So we have N air times sine of the incident angle, which we know, is equal to N water, which is the other side of that change in medium, times sine of the refracted angle. We happen to know N water and N air. N air is always 1, N water is 1.33. So we can solve for θ2. And numerically, it would give us 41.842 degrees. Now to finish this off, we need to get the total horizontal distance, L, which is equal to the horizontal distance before the light hits the water, plus the horizontal distance when the light goes through the water. If we know these angles, we can know everything about the two right triangles that we need to get these two bases. So we can set this up. Okay, L1, we can express L2 as just H2 tan of that second angle. And finally get us to 2.5 meters, which we already know, plus 2.1 meters, which is the depth of the water, tan of the angle, which we know, tan of 41.8 degrees. And just doing this number crunch, adding it up, we have 4.38 meters, which is the total length that the light travels horizontally from the flashlight through the water until it hits the bottom of the pool. And that's it.